Okay, here we are. Let's talk about the physics of light for plant production. So, light has three different qualities that we're going to talk about. Quantity, how much light is there, duration, for how long, and then quality, what kind of light was it? So as light is coming in and striking an object, maybe this pane of glass, three things occur. The first is that it can continue to transmit and just pass entirely through. Light could come in and go through the glass. Nothing's changed. There can be some reflectance. Light's coming in, part of it's hitting, part of it's going through, and part of it's reflecting and coming back up. That's why when you are looking through a window, you can still see something because the light's coming in, going through the window and hitting your eyes so that you can see what's outside of it. But also, you get that kind of glare, that shine. That's light coming in, hitting the window, and bouncing back off. And then the final thing, being absorbed. That's light coming in, hitting the window, and not going any farther. Not reflecting, not transmitting through, but just being absorbed into the material. So even a clear object like glass is absorbing some of the light that's coming in. And so again, if we look through this window, you can see the outside because of the transmitted light. You can see a reflection because of the reflected light. And then you can feel a warmth to that glass as it absorbs some of the light as well and gains energy from that absorbed light. So this is what can happen to light as it comes along. Just three different ways. As we're shining light at something, it can scatter, it can bounce, it can be absorbed, it can continue. That's what can happen to light. As we get back to talking about light, or these aspects of light, the first one would be quantity. How much light is there? So light exists in this weird space of duality. So first we've got this wavelength, electro wavelength. Then we have a magnetic wavelength. So a set of double waves. Waves going this way, waves going this way. Then it's a particle, right? A particle of waves, because this is one photon. Light can, and typically is, many more photons. So if we were shining like a flashlight from here, we would be shooting out a bunch of photons. It's not just one beam of light that is one photon. We have a particle of waves, many of them. So here's our quantity. Quantity, how many photons? We can kind of think about the number of photons as in the light intensity. How many photons there are tell us or will affect how brightly we can see things. If we have a flashlight only putting out 100 photons, it's going to be, this amount of bright. However, if we put out 1,000 photons, well, that's a lot brighter, right? However we're showing brightness, that's so many more. It's 10 times as many photons coming out and lighting up the world and being able to hit things, be absorbed by them, bounce off them, reflect into our eyes so that we can see them. So now that we know that light is made up of discrete pieces of photons, just like when you turn on a hose and water's coming out, it's not just an infinite amount of water that just goes forever. There's individual little pieces inside all that water are water drops. And then of course, inside each water drop is a water molecule. Well, same with a flashlight. You turn on a flashlight, it's not infinite light. It's a certain number of photons. Like you cover a part of the flashlight and that's fewer photons. And we can really drill down into just finding how many photons are coming out of a certain place. However, so since it is a discrete number of photons, those photons can only go so far, just like a gallon of water can only water so many plants. 1,000 photons can only light so much space. So we've got something called the inverse square law, which is incredibly important when we're talking about lights for plant production. There it is, inverse square law. All right, so we have a light source here at S, and these are photons. These red lines are tracing photons as they head out. And then these r's are distances. So r is the first distance away from the light, 2r is 2 times the distance away from the light, and then 3r is 3 times the distance away from this light. So you can see at 1r, all these photons are hitting that one square. Now we take it out to 2r, same number of photons, same source light, same number of photons, same number of red lines. But now we're hitting 4 squares. All those photons are spread across, instead of one square, they're spread across 4 squares. So this is where we get the inverse square law. This first r, at 1 distance away, we cover, let's say, 1 square foot. At 2 distances away, we cover 4 square feet. So it's the inverse square. It's square because it's the distance away gets squared across the area that the photons are spread, and then it's inverse because there are fewer of them. So, here we got 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 dots of light, 9 photons passing through this first square foot of space. As we get further away from the flashlight, as we get twice as far, we have those same 9 photons, but they're now going through 4 times as much space. Twice as far, 4 times the area. So there's the inverse square. 2r, inverse it, 1/2, square it, 1/2 times 1/2 equals 1/4. So we have 1/4 the photon flux density, right? The number of photons here, it was 9 per square foot. Now we have 2 to 3 per square foot, and so 9 times 1/4. Let's see here. 9 photons at 1/4 of the density anymore equals 9/4, 2 1/4. And that's what we got, right? Between 2 and 3 photons per unit space. So that is, like the inverse squared. We had 9 photons, we had 9. Then we had to inverse square it. So we doubled the distance, which means we quartered the density. 9 became 2 1/4. Now, let's move one more time down to this, let's see here. There we go, down to this 3r. So now we're further out yet again, right? That's across 9 square feet. Across 9 square feet. So we have the original 9 photons, right? 9 beams of light. So now we have this 3. First we flip it, inverse, 1/3, and now square it. So times itself becomes 1/9. So 9 times 1/9 equals 1. So here's the, if you can see it in the picture, this is what's happening. We go from 9 photons, to barely 2 photons at twice the distance. And then double that distance again, we're down to 1/9 of a photon. So do you see a practical application for this yet? What does it mean? We have a source light, and the light is becoming more diffuse, less concentrated across that distance. We want to put our light as close to our plants as possible, because really, full sunlight is equivalent to about 160 watt bulbs. So that's a lot of bulbs per square foot, per square foot. So we're trying to jam 160 watt bulbs into a square foot to replicate sunlight. That's really hard. That's almost impossible. And so instead, because we are providing these lights, because of this inverse square law, because of how the light we provide becomes more scattered and less strong as the distance increases, we want to put this light as close as possible to our plants. So that's, if we had, it's like having, we have a light here. This light, if they're the same amount of lights, this light is barely hitting those plants, right? But then, again, we bring the same light down in closer, and now we're seeing it's missing a little bit, but it sure is hitting a whole lot more. Okay, let's move on to duration, or how long the light is on. After discovering quantity and photons, we can see individual photons are what's coming from light sources. That leads into, pretty simply, I think, that the duration, how long you have light shining on something, affects how many photons there are hitting it. So just like watering a potted plant with a quick blast of water is not the same and does not deliver the same amount of water as leaving that hose on for a minute or 10 minutes. That duration, it's delivering the same amount of photons per unit time, but you're giving it more time, so it's got longer to deliver those photons. And we can see it in, hopefully this picture makes sense to you all. So let's imagine some wood paneling on a floor beneath a sunny window. As it starts out, it looks like this. But as the years go on and the sun continues to shine on that spot of the floor and not the rest of the floor, we see the wood paneling begin to fade and begin to fade. And by the end, it's really, really sun bleached. So this could be how the wood paneling, your wood floor looks in the rest of your house. But as you get near the window, as it's had a long duration, so this spot, the far spot, might receive light 16 hours every single day, where this spot maybe gets light 1 hour a day. And so that's just compounding across time. 360 days in the year, this wood is very bleached. It's had an extremely long time of its exposure to sunlight has a very long duration. Lots of photons have been hitting it. So now the number of photons, how long the light's been shining, so again, how many photons, and now finally we get to the quality of those photons. What kind are they? What kind of photons are they? Right? So this classic idea of a prism, if we have white light coming in, it can be split into different kinds of light because all this light is actually contained within white light. And so this is where we get to quality of light. So the quality of light isn't, how good is the light bulb? How much money did you spend on the fixture or anything? This is the wavelengths or the color when we're talking about light for plant production. So that when we say, the quality, what's the quality of this white light? Because to you and I, we can get white light a number of ways. You and I would probably still see white light even if maybe, let's say this chunk was missing. This whole chunk was missing. Or this little band was missing or something. Like we could take colors out of this light, and to our human eyes, it would still look like white light. So this is why we need this quality assessment. Don't just tell me, it's white light. Give me a breakdown of all those colors. Show me a spectrum reading. What kinds of lights? What's the quality of that light? What is my quantity? How many photons do I have for each of these qualities, for each of these wavelengths? All right, now bringing this to a close, we're circling back to the beginning of the lecture, remembering those 3 different things that light can do as it is cast. Here we have light transmitting and passing through. You could even have, this reflection, a little bit of reflection, right? Light bouncing off, and then a little bit of absorption. Can't really see it, but the light got absorbed by this prism. When we are trying to supply light to grow plants, we want to cut down on as much of this reflection as possible because we are paying for this light to show up. We don't want it to bounce off and not reach our plants. Well, that was the idea of reflection right there, right? Light comes in, gets reflected back, but we have the idea of adding reflection control to our growing environment. So here are some common materials used to focus and reflect the light provided to a plant back onto the plant itself. We've got space or emergency blankets, mylar blankets, whatever you want to call them, just using flat white paint on the surface, using a semi-gloss white paint, flat yellow paint, aluminum foil, and black fabric, just as a reference. So do any of you have any guesses? Do you have a preference? Do you think which one of these do you think is going to do the best? And which one is something that you've used? So first up, best one, space or emergency blankets, reflecting almost all the light coming in, just reflecting it, not absorbing it, not letting it transmit. Flat white paint does very well as well. Semi-gloss white paint, that's bringing some of that reflection back in. This gloss is reflection that you and I are seeing, that shine is light bouncing off it. So if you're trying to focus light on a plant, you don't want to use semi-gloss, you want to use flat. Then we come around to flat yellow paint. Still pretty good. Aluminum foil, really starting to dip. We're at less than 25%, or a full quarter of the light isn't actually being reflected by aluminum foil. And then of course black. A black surface doesn't reflect light, less than 10% of light. So obviously the clear winner seems to be space emergency blankets, but the point that I want to make right now is about this aluminum foil. Really, the point is no, or maybe don't use it. Aluminum foil is conductive. It can conduct electricity, and when you're using it to block light, especially with plant production where it's a moist environment, a high humidity environment, that's increasing conductivity potential. This is bad news. This is a terrible, non-safety. What's that? Dangerous, non-safety. It's dangerous. I understand why. It's very cheap. It's super accessible. I'll even confess to you that I've used it. But I want to point out to you, beyond even if you want to ignore the safety concerns and say, I know what I'm doing and I'll be good. Look at it here. There's everything else. There's so many things better than it. It's missing 25% of the light that you're trying to bounce back at it. Emergency blankets, Mylar blankets, they're not that hard to get. Flat white paint is cheap, easy to apply. I mean, even flat yellow paint, not too great compared to the others, still at least an average of aluminum foil, maybe better. But so, you could use flat yellow paint, not gain any additional light reflected, and still be safer. I guess that's my point. Don't use aluminum foil. Use another option. Thanks for listening to the physics of light for plant production.